What's up, everybody? Here is the part 2 of the derivative section, which is, I guess, section 3, and we'll start with problem 13 now. So for part A, we're asked to find the derivative of f of x is sine of x cosine 5x, right? We have a product of two functions. Obviously, we're going to need to use product rule, so we have cosine of x cosine of 5x plus sine of x times negative 5 sine of 5x, right? It's negative 5, or this 5 in front comes from the chain rule application, and that's the derivative. For part B, we're looking at the function g of x is square root of natural log x minus 4. So g prime, that's going to become, let's see, the outermost function is the square root function, so we're going to end up with 1 over twice the root of whatever's inside, so ln x minus 4, but we have to multiply also by the derivative of the inside by chain rule, right? So that's going to be 1 over x minus 4. So that's the derivative there. And the last one, part C, this is h of x equals e to the 5x squared times arctangent. So again, we have a product of two functions, which means we're going to invoke product rule. So h prime of x is going to be the derivative of the first now. That also uses heavily chain rule. So we have e to the 5x squared, but we multiply by the derivative of the exponent, which is 10x times arctan plus e to the 5x squared times the derivative of arctangent, which is 1 over 1 plus x squared. And that's the derivative, that's it. And of course you could factor out the exponential, whatever. I'm not going to bother simplifying these, I'm just going to do the calculus. So that's problem 13. Let's move on to problem 14 real quick. And we're told to find the derivative for f of x equals arc cotangent of x. Okay, well, let's start with writing y equals arc cotangent, and there's nothing I can do here, so instead what I'm going to do is I'm going to apply cotangent to both sides. So I have cotangent of y equals x, since arc cotangent is the inverse function of cotangent. And now I take the derivative of both sides with respect to x. So let's see what I end up with. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. Y times dy dx, right? That comes from chain rule. And that should equal to just 1. Okay, excellent. So that means I can solve for dy dx. That's going to be 1 over negative 1 over cosecant squared of y. Okay, so far so good. But now I would like to go back to variable x. So for that we're going to need a trig identity. If we know that sine squared of x plus cosine squared of x equals 1, what I can do is I can go in two directions here, right? I can either divide by cosine squared, so I end up with tangent squared of x plus 1, right? Cosine squared over cosine squared equals 1 over cosine squared, so secant squared. But that's not the identity that I'm looking for. I'm looking for the other one where I divide by sine squared. So now I end up with 1 plus cotangent squared of x, right, because I end up with cosine over sine, which is cotangent, equals, and then I have 1 over sine squared, which is cosecant squared of x. So this is the identity that I'm looking for, and when I apply that, what I get is that dy dx is going to be equal to minus 1 over, and now cosecant of y is going to become 1 plus cotangent of y, squared of course, but we know that cotangent of y is x, and that allows me to go back to my variable x using this piece right here. So this is minus 1 over 1 plus x squared, and that's the derivative of arc cotangent, negative 1 over 1 plus x squared. Okay, number 15. This is just some implicit differentiation stuff. I'll skip part A because that's an easy one. Let me do part B, which is a little more complicated. So I have x y squared equals 7x to the 4th plus 2x plus y, and we need to find dy dx using implicit differentiation. So let's take the derivative of both sides with respect to x. Here I end up with, I have to use product rule, so 1y squared plus x 2y.
This is going to give me 28 x dx. And just like any implicit differentiation problem, I want to move all the terms that have dy dx on one side, all the terms that do not on the other. So I'm going to have dy dx, let's factor it out. I'll have 2xy from here minus 1, because once I move it to the other side it becomes negative, equals 28x cubed plus 2 minus y squared, which is that term. Okay, and then I simply divide by 2xy minus. Let's quickly do part C. I'll do it on the side here. I think I have enough room on this sheet of paper. So I'm looking at e to the xy equals xy plus 1. Let's take derivatives with respect to x. So the derivative here is going to be e to the xy times the derivative of the exponent, and this is where I have to use product rule. So I have y plus x dy dx equals y plus x dy dx, another application of product rule to the function xy. Okay, we have to distribute the exponential, and then we have to move this to the other side. So what I'm going to end up with is dy dx. Over here what I'll have is x times e to the xy minus x, once I bring this over from the other side. And this is going to be equal to y minus y e to the xy, right? That comes from, once I distribute this over, so that means dy dx should be equal to, just take the fraction, right? Y minus y e to the xy over x minus, x e to the xy, but I want to bring it, I want to write them in the same order, so x minus x e to the xy. And once I factor a y and an x, notice I get 1 minus e to the xy both on top and the bottom, so this should be negative
y 1 minus e to the xy over x 1 minus e to the xy. So those things cancel, which means dy dx in its simplest form is negative y over x. So that's the result there. This was the result for the previous part. And that's problem 15. So now let's move on to quickly do problem 16. Or actually, so for 16,
curve plus y squared equals x minus y plus 6, and I want to find the slope of the tangent line at the point 2, 1. So I already have a point, I just need the slope, which means the steps are find dy dx using implicit differentiation, and then get the slope by plugging in x equals 2, because it's going to be a formula depending on x and y equals 1, right? The coordinates of our point. So once you have the slope, then you write the equation of the line. I'm not going to do it. This should be fairly straightforward. What I do want to do is look at problem 17, right? So we have a particle that's moving along this ellipse, which is x squared over 4 plus y squared over 12 equals 1. So I have a particle moving along this. We're not told which direction, but it doesn't matter. And I know that as the particle passes through point square root of 2 and square root of 6, we're given that the velocity in the x direction is square root of 3 units per second. So automatically, when I translate that into math, that says that dx dt, it is going to be with respect to time, because it's a velocity, it's going to be positive root 3. So the point is somewhere here. The velocity in the x direction is like that, which means the point has to move in that direction, like that. So the question is, what is the velocity in the y direction? And the way we do that is we take this equation and we take the derivative with respect to x, right? So once I do that here, I get x over 2, because I have 2x squared, I simplified the 4, plus y over 6, right, because I have 2y simplified by that, times dy dx. I'm sorry, not dy dx. I should be doing this with respect to t, my bad. So it's x over 2 dx dt plus y over 6 dy dt, my mistake, equals 0. I know the x value, that's root 2, y is root 6, and I know the x dt is root 3. So I can just solve for the unknown in this equation, and that's how we do this problem. For problem, let's now move on to problem 18. So problem 18 is one of those solids of revolution problems, and we're told the following, right? We're told that a tank of water is obtained by revolving the region y equals x squared, the region bounded by y equals x squared, and y equals 4, right? So we're revolving this region about the y-axis. And we're told that water is added to the tank at a rate of 1 cubic meter per second. So instead of doing this at
all the way up to 4, what I want is I'll do it for a general depth d, and I want to find an equation involving d and the volume of water, right? So I have d is the depth of water, v is going to be the volume of water, so it's going to be changing as you add.
We know, we're told, we're given a dV dt is 1 cubic meter per minute, right? And we want to find what is the derivative of the depth when d is equal to 1. So this is what we're looking for here. Okay, really quickly we can set up an integral for that. It's revolved around y, so I need a cross-section along the y-axis. So notice now the radius of this is going to be the x-coordinate on my parabola, right? Once I project that down, that's the x-coordinate, and that's the square root of y, and I'm revolving that about y, so the volume is going to be given by the integral as y goes to 0 up to y equals d, the depth, the total depth of pi radius squared dy. So this is going to be the integral from 0 to d of, let's see, what do we end up with? What we're going to end up with is, let's think, r squared is going to be just y, so I have pi y dy. So now this is going to be pi over 2 y squared evaluated from 0 to d. So it's simply pi d squared over 2. That is the volume at depth, when water has depth d, for this parabola, or for this paraboloid rather. Okay, so we have an equation relating volume and depth, and I have some derivatives. I'm given some information about a derivative with respect to t of both these variables. So let's differentiate both sides of this equation here with respect to t. On one end I'm going to have dv dt, and the other end I'm going to have pi d dd dt. Okay, the 2 comes down, canceling the 2 in the denominator, so I'm left with just pi d to the first, and by chain rule I multiply by the derivative of d with respect to t. And let's see, what do I know? I know that v is equal to 1, d is equal to 1. I need to find dd dt, so dd dt should be 1 over pi. That's the answer, right? And I guess the unit would be meters per second, since the volume was given in cubic meters per meters per minute rather, because the volume was given in cubic meters per minute. So that's problem 18. Let's go ahead and look at problem 19 now. Let's see, we have an isosceles triangle, so let's start drawing the pictures and labeling things. So we have an isosceles triangle with vertex angle theta, and we're told that this angle increases at a rate of 1 radian per minute, right? So that's positive 1. I'm sorry, it's decreasing, my bad, I misread.
So the rate of this is -1 radian per minute, and the length L of the legs of the triangle is increasing. So I have that dl dt is increasing at a rate of 3 centimeters per second. This was per second too. Okay, excellent. And we want to know how fast is the length of the base, so let's call that B. How fast is that changing when theta is pi over 3 and when L is √6? Okay, so notice if theta is pi over 3 and L is √6, that means we have an equilateral triangle at that moment in time. So that means B is also √6, and that's going to help us save a little bit of time later on, because we will also need the value of B. Okay, so how do we go ahead about solving this problem? What I want is to relate all the three variables together. So let's drop the height in this triangle, and let's copy down half of what we get, right? Let's copy down one of the right triangles that we get. This is going to become B over 2. This is going to become theta over 2, and this is still going to remain L. And now I want a trig function that's going to relate I guess these three variables together. So what I can do is, notice this is the opposite side of the angle, and that's the hypotenuse. So I can start with the equation sine of theta over 2 equals B over 2 divided by L, so just B over 2L. And that's the equation that I have that relates all three variables. And I can start, since I want to find the rate of change of the length, let's take the derivative of this with respect to t. So on one end, the derivative of sine is going to be cosine. So let me write that down here. Cosine of theta over 2 times a half by chain rule, d theta dt. And that's going to equal, now I have to take the derivative of this fraction where both the top and the bottom are functions. So I have the derivative of the top times the bottom minus the top, so just b times the derivative of the bottom. All divided by, what do we have? Divided by the bottom squared, so 4L squared. Okay, so what do we know in this formula? I know theta, I know the theta dt, so that's good. I know dl dt. The unknown is this dB dt. Okay, so that's the thing that I'm trying to solve for. I know L and B, and cosine of theta over 2 is going to be cosine of, since theta is pi over 3, this becomes cosine of pi over 6, and I know the angle for that. I know that's going to be √3 over 2. So once I plug in everything, right, I can easily solve for this. The rest is just algebra. I'll let you guys do that on your own time. That's problem 19. Let's go ahead and do problem 20, right, which is a linearization problem, and we're asked to approximate the value of square root of 3.9 first. Well, let's do this one first, and then we'll have to do the cosine of pi over 5. Okay, so I can approximate this by using the function f of x equals, let's use square root of x, and I want to find the linearization at a equals 4. The reason why I pick 4 is because I know the square root of 4 is going to be 2. So I pick a value of a for which that is close to 3.9, for which I know the function value at. Right? Let's take f prime. F prime of x is 1 over 2 root x, and when I evaluate this at x equals 4, I simply get 1 over 4. Okay? So now the linearization is going to be f of a, in general, this is the formula, plus f prime of a times x minus a. So for our particular function, the linearization is going to be, okay, f of 4, that's just 2 plus a quarter x minus 4. And to approximate this, the square root of 3.9 is going to be approximately L evaluated at 3.9. Okay, so when I plug in, what I end up with is 2 plus a quarter 0.1, negative 0.1, my bad, because I'm subtracting 4. So this is going to be 2 minus 0.1 divided by 4 is 0.025, right? So this is 1. What is it? 975, I believe, if my algebra is correct. So that's the approximation there. For the second part, we want to approximate cosine of pi over 5, right? So obviously I'm looking at f of x is cosine of x, and the question is, for what a value do I want to find the linearization? So I need some x value for which I know the value of cosine that is close to pi over 5. So the options are either pi over 4 or pi over 6. And it turns out that pi over 6 is actually a little bit closer. So that's the one that we should be using. Then the process is the same. I take f prime of x, that's minus sine of x, and when I evaluate that at pi over 6, I already have this little right triangle here. Pi over 6 is this angle here, sine is a half, so this is negative a half. And the linearization formula is going to be cosine of pi over 6. So cosine of pi over 6 was root 3 over 2. Minus a half, minus because that's negative, x minus pi over 6. Right? So then cosine of pi over 5 should be approximately, let's see, I just plug in pi over 5, so root 3 over 2 minus a half, pi over 5 minus pi over 6. Okay, perfect. So that, you plug it in, you do the algebra, or you can just use a calculator, you get some approximate value for this using the linearization. So that's problem 20. And really quickly, I'm not going to do all the details, but I do want to talk a little bit about problem 21. Okay, so for 21, we're asked to find the linearization of the function arctan of x, and we want to find the linearization at a equals 1 and at a equals root 3, and we want to use this to approximate. We want to use both linearizations to approximate arctan 7/5. Alright. So the process is the same as in the previous problem, which is why I won't go through it. What I do want to talk about is the second part of the question: which is a better approximation, right? Is this a better one or that? Now I know the graph of arctangent, at least for positive values, looks something like this, right? And there's an asymptote at pi over 2. So that's arctan of x. And I'm looking at a equals 1, so I'm looking at a linearization there. And I'm looking at a equals, let's say, root 3 is somewhere over here. Okay? Now root 3, by the way, is, I believe it's 1.7 or something, right? And 7/5 is 1.3, right? So I have 1, I have 7/5, and then I have root 3 in that order, which means 7/5 falls somewhere. Not 1.3, this is, my bad, this is 0.13. Oh no, I'm doing this wrong on the calculator here, 1 second. 7/5 is 1.4. I don't know how that happened. Okay, 1.4, root 3 is 1.73. So notice the difference here between 7/5 and 1 is going to be 0.4, whereas the difference here is going to be much smaller, right? It's about 0.33. So that means the 7/5 lies, and I'm going to exaggerate it in the picture, closer to the root 3. Now remember, we were trying to approximate this value here, right? F of 7/5 using linearizations. And the way linearizations work is I simply take the tangent line equation and I project that, and I get some sort of picture like this. Okay, so the orange line is the linearization at a equals 1, and this purple line is going to be the linearization at a equals root 3. So let me just make that clear over here. Now when I project these lines, right, the approximation is given by the distance between this and the function. So notice I have a much larger error for the a equals 1 than I do for the a equals root 3, because this tangent line is closer to my point, right? The purple tangent line is closer to my point. I'm not sure if you guys can see color in the video over there. It's a little bit faint, but the point is that because this is a concave down function, and 7/5 is closer to root 3 than it is to one. Because of these two facts, the linearization at a equals root 3 is going to give us a better approximation. So that's the second part of the problem, and actually that finishes off section 3, which is the derivative section.